In this video, we're going to cover balanced three-phase power analysis, which is relatively nothing new other than applying what we already have known to the three-phase balanced circuit. Let's take a look at Y-connected load, and then when we're finished with that, we'll go take a look at the delta-connected load. So, as we know, just a general equation for real power, real or average power is equal to voltage times current maximums times cosine of theta V minus theta I. So we can apply that to this circuit because we know that Vm is basically the phase voltage, is the magnitude, so would be the magnitude of VAN, and that's represented by the phase voltage as V of phi. Then they're exactly the same for all three of them. So this really we can replace by V phi, and then when we take a look at Im, that Im is going to be pretty much this is the line current and line voltage in the case of Y. So their magnitude of all of these will be also I of phi. So therefore we can go ahead and replace that with I of phi regardless of which one we are calculating. And then the angles really depend on which phase we are looking at would be the only thing. And since they are moving in the same each phase, the I and V relationship is the same. So in other words, if we have a phi for a theta for a phase, that is going to be the same for A, theta I of A as theta V of B minus theta I of B, the same as the theta V of C minus theta V of theta I of C. So all of a sudden, regardless of which phase, it really doesn't matter which phase we are looking at, each one of the phases, whether it's phase A or power for phase B or power for phase C, all of them is going to be V of phi times I of phi times cosine of theta phi. So that allows us to be able to make the statement that the total real or average power for a three-phase circuit can be written as P of total equals to sum of all of these P's, which basically turns into 3V phi I phi cosine of theta phi. And that's a nice equation for us to remember. We can even use the same technique and apply it to the reactive side. But before we go to the total reactive side, we could also do the same thing, but instead of using the phase voltage and phase current, use the rule we had, which was a square root of 3 process, and replace these with a line voltage. So we can write this in terms of line voltage and line current if we wanted to, by just basically saying, okay, we know that V of phi over square root of V of line over square root of 3 is equal to V phi, and we can go ahead and leave I of phi, I of line are the same thing for a Y connected, and then cosine of theta phi stays the same. So you could potentially write P of t in terms of line voltage by just saying square root of 3 V line I line cosine of theta. That's another way of writing the total power. Of course, if you're interested in writing the Q, both of these will be able to convert. The same process would work for what we had done before. The only difference is that we have to replace these cosines with a sine. So we can literally say that the reactive power Q for total for the three phase, you could write it potentially as either 3 v phi I phi sine of theta phi, or we can write it in terms of the line voltage, which is square root of 3 VL IL sine of theta phi. So these are somewhat useful to have. We could also write the complex power per phase if we wanted to, taking advantage of the fact that the complex power is voltage times I conjugate. So we could just simply say V of IN times I AA conjugate, and that's kind of useful as well to do that. And again, this will give us the result, which from here we can find a V of phi plus J Q phi as well. And of course, since regardless of which phase we do, we're always going to end up with similar equations, we could also summarize this whole thing to say, okay, and from up here and up here, take these values. We can say is equal to 3 phase is equal to this total. All three have the same power, so the total complex power, total complex power is equal to 3S phi, or you write it in terms of line voltage, square root of 3V line voltage, I line voltage with this shift of phi. So these are multiple ways of doing that. We can also take that same process and same thinking, and this time take a look at a delta connection. This is a redraw of a delta connection. And then in this case, we know that the phase voltage and the phase currents are the same, so we literally can start with the real power and imaginary power, reactive power, the way we worked it. So if we start by knowing that in this particular case, the V of phi and V of line are the same thing, and that from a magnitude point of view, and they're going to be equal. Doesn't matter whether we're looking at AB or we're looking at line voltage at BC, or we're looking at line voltage at CA, BCA. They're all going to be the same, and V phi, you don't need to have a magnitude on this. So VL and V phi are the same, and all the magnitudes are the same. And when we look at I of phi is going to be basically the magnitude of the phase current, the currents that run through the phase, and then the difference in theta phi, the difference between V and I is going to, again, the same as before, it's going to be the same. So theta, for example, VAB minus theta IAB is going to be the same as the angle BC minus theta IBC, same as theta VCA minus theta ICA. So those are all going to be the same, and if we follow the same procedure that we've done in the previous case, we will find out that total real or average power is going to basically be the same as what we had before, which is 3 V phi I phi cosine of theta. And if you want to write it in terms of a line voltage and current, it's going to be VL IL cosine of theta. So, and that's, again, the reactive power, we can do more or less the same thing we've done. I just replace the sign with the cosine and you get the same thing. So in the case of reactive, this is the reactive power. QT is going to be 3 V phi I phi sine of theta, or square root of VL cosine theta. I'm sorry, sine theta. This is the reactor. Okay, and then of course the total complex power it's gonna be the same as before. S total is equal to 3s of a phase, and we remember that this complex power of a phase is gonna be V of a given phase, any of them, then times phase V of one phase times I conjugate of that phase, and we're gonna have to have 3 of these. So that's the way. And then of course this whole thing is basically P plus JQ. So multiple ways of getting to the total power, either by individually calculating these two and plugging it in here, or directly going to application of the values. Sometime you may also see this whole thing written as square root of 3 VL IL angle of V. That's the difference between I and V and the V. There are lots of formulas here. Most of them are just basically from you understanding the basic configuration and applying power relationship we've learned in previous discussions of phasor and phasor diagram and phasor power. So here is a delta connection, and here is a Y connection, and then we have the appropriate equations for each one of those two cases. One is here and the other one is over here. So this is the delta and this is the Y set of equations.